Okay, so onto the pathfinding part of this lab, we explored several different types of pathfinding algorithms. The first of which are the graph search ones, such as A-star, Dijkstra's, BFS, and DFS. And graph search algorithms are going to be very computationally expensive because we have to search over the entire occupancy grid, which is made up of hundreds of thousands of nodes. So we also explored sample-based search algorithms, such as RT-star and PRM-star, and these are much more efficient because they're only searching over a small subset of randomly sampled points from the entire graph. And so we chose to implement a probabilistic roadmap with A-star search on top of that. And so the advantage of this is we have very fast pathfinding. We are combining the strengths of A-star search with a heuristic to find very quick paths, with the fact that it also only has to search over a small amount of nodes as opposed to the entire graph to give us a very fast pathfinding algorithm. And we also can have multiple queries, so we can have a start or end point anywhere in the path, and it'll be able to find a path between them. And it will also generate optimal paths, provided that we have a large amount of nodes in our probabilistic roadmap. The disadvantages are the paths that it's going to generate are often going to be segmented and disjoint because we only have a fixed amount of nodes in it. There's going to be a large amount of pre-computation. It takes us about 50 seconds to generate our PRM before we're able to use it. And it's only going to work in a static environment. So the locations of the collisions can't change. Otherwise, we have to regenerate our PRM. And so in order to generate our PRM, we first need to figure out where we're allowed to place nodes. And basically, this is just going to be any spot that's not a collision. And so we first dilate every collision in our map by a factor of 10. And this is going to help prevent nodes from being placed near collisions, so that the pathfinding algorithm will have a margin between collisions so that it won't cut a corner too close to a collision and then the robot will run into it. And so we randomly sample points and insert a node anywhere in the free space. And then whenever a node is placed, it's going to connect an edge between all neighboring nodes within a certain radius. And this radius is going to be determined by a constant and also the number of nodes previously placed. And it's going to fall off as log of n over n. And this factor is important because it's the part that allows our algorithm to become asymptotically optimal with the amount of nodes placed. And so this is an example of a PRM with 2,000 nodes. This is typically what we use to run our search on. And with this amount of nodes, the paths are roughly complete. And well, the paths are complete and they're roughly optimal. And so to search over the PRM, we first insert the start node and end node into our PRM, and then we just run graph search or A-star search over the PRM between the start and end node, and then it returns the path, as you can see here in yellow. And so now on over to KJ to talk about the A-star algorithm.
So as Sam mentioned, we used A-star pathfinding to find the optimal path to the goal, as opposed to more simple techniques like breadth first search or depth first search. A-star will be able to find the path quickly because it uses a heuristic in addition to the edge weights to find that optimal path. And with A-star, everything's really as good as that heuristic. So the specific heuristic we used was the distance to the goal. Here, for each node that's explored, we're going to add up the cost, as usual, into this G value. And for each point, we have a total cost where we add this G value to H, which is our heuristic. And in our case, the heuristic is just, as I said, the distance between the point to the goal. And the Euclidean distance is just that straight line distance. And keeping track of costs along the way, just make sure that we tend towards the goal and don't traverse these other branches that deviate. So we also wanted to make sure that the car could actually make the turns that we set out in the path. So we constrained our path to allow for the car to have its turning radius within that angle between the two edges. And as a result, the path that we generate is feasible in terms of the car should still be able to traverse on top of that path and shouldn't have to make any corrections based on its turning radius.
The pure pursuit path tracking algorithm works by calculating the curvature to navigate the robot from its current position to its goal position. Analogous to how when you're driving a car, you keep your eyes fixed on a certain location ahead and you control the steering angle to reach that position, pure pursuit works by controlling the steering angle of the car to navigate to a goal position that's a variable look-ahead distance away at a fixed speed. The pure pursuit algorithm has four main parts. The first part is the localization of the robot. The second is finding a path point that is closest to the vehicle, and then finding the goal point from that path point that's a certain look-ahead distance away from the robot. The last part is to actually calculate the curvature and set the desired angle of your robot to reach that goal position. To find the path point closest to the vehicle, it's basically a problem of finding the shortest distance from a point to a line. The trajectory is represented as XY coordinate pairs, and when you draw a line between each of those segments, you have your path. So you need to calculate the shortest distance from the robot to every single line segment along that path, and then the minimum of those shortest distances is the closest point to the vehicle. So this is visualized in RViz with a purple dot, and then once you find the closest point, you travel along that line segment that the closest point is on to find the goal point that is a certain look-ahead distance away from the vehicle. Finding the goal point is basically finding the intersection of the line segment that is your path and a circle that is of radius goal distance or look-ahead distance. So as you can see by this picture, Q would be the location of the robot, R is the look-ahead distance, and you have three different cases of what can occur. So the first is when you have two intersections, it means that there are two locations on your path that are a look-ahead distance away from your robot. In that case, you just choose the path that is the closest to the final end point of your path, which is what we did. If there's one intersection, you navigate towards that one intersection. If there's zero intersections, we handled it by setting the goal point as the final destination point, and then we navigated towards that point. The last part is to calculate the curvature and the desired steering angle. This is done by following the equation given from lecture slides. In our case, the length of our robot is big L, which is 0.325 meters, and L forward is the length of the robot divided by 3, which calculates a certain distance forward from the rear axle of the robot. We are solving for delta, which is the desired steering angle of our robot, to follow the curvature that would lead it to its goal point calculated previously.
Pure pursuit code could respond differently based on what we set the look-ahead distance to. As can be seen in the graph, this meant that a longer look-ahead distance resulted in a smooth, longer curve for the robot, which is good for straight paths, but not as good for following complicated, curving paths, where a smaller look-ahead distance might be better. To make our pure pursuit code more flexible to different environments, we set the look-ahead value to be a function of some other variable. The three variables we looked at were dx, which is the distance between the goal point and the current position in the x-axis, theta, which is the angle between the goal point and the current position, and curvature, which is the curvature of the path, or the inverse of the radius of curvature. All these values were given a minimum of 1.5 and a maximum of 3 to prevent getting just weird values. We settled on using the curvature as our variable for the look-ahead distance, although all three yielded similar results, which were successful. As can be seen here, our pure pursuit could follow a given path almost exactly. The green path is underneath this path here, and it pretty much can barely be seen except like in the corners. And here's an actual demo of our robot planning out a path and then proceeding to follow it. Now it follows this path pretty closely, even around this curve. So to conclude, using an A-star search algorithm with a pure pursuit code whose look-ahead distance was dependent on the curvature of the path, we could successfully plan trajectories and have our car follow them.